When we study chemical kinetics is the study of rates of reaction. How fast does a reaction proceed from reactants to products? And the topics will be rate factors, rate laws, rate in the kinetic molecular theory, and the effects of catalyst on the speed and nature of chemical reactions. Is the study of rates of reaction. Now, this represents one of three major concepts in the study of chemical reactions. In the study of chemical reactions, we use chemical kinetics, two, chemical equilibrium, and chemical thermodynamics. Chemical kinetics, as I just mentioned, is, of course, the analysis of rates of reaction. Now, when we get there, you'll understand this in a moment, what chemical equilibrium is. Chemical equilibrium is extent of reaction. That is, as it starts and goes to a point where it enters an equilibrium. Some take a long time, some almost instantly reach equilibrium. That's what we call extent, and I'll have a graphic here that illustrates that and shows you how that fits between kinetics and equilibrium. Thermodynamics in itself is a study of the feasibility of a reaction. That is, simply, will the reaction go to products or will it not go to products under the conditions that are specified? You can use thermodynamic principles to determine that and then design your engineering environment to support whatever you're trying to do, and there's a strong probability that you will be successful. So as we start our work on chemical kinetics, we need to understand what factors affect the rates of reaction. And then apply those factors to what we call rate laws. So we call it a rate factor proportional to a rate law. So we'll build rate laws out of these. These are mathematical expressions that give you indications of the speed of a reaction. Now, just before we do that, we need to look at what reaction rate is. In chemistry, by definition, we're talking about a change in concentration per unit time, change in time. Now, in chemistry, concentration terms are measured in terms of mole per liter, molarity. Of course, time is in seconds. So when we put this terms into the definition of rate, then we have reaction rate units is molar over seconds, or moles per liter divided by seconds. And just put S. Now, what you'll find in the data, and you'll see this as we get into it, is a unit of rate will be molar per second, or moles per liter times seconds. In other words, this has just been inverted and multiplied back into the numerator. Or you will see moles dot liters to the minus 1 dot seconds to the minus 1. So you'll see these pop up on problems as you go through and study those items, but they all mean the same thing, and they all relate back to the idea of speed, rate. Keep in mind that when we talk about rate in physics, of course, it's miles per hour, feet per second, and so forth like that. Well, it's no different in chemistry, but we have to have a term we can measure, and of course that is concentration terms. And so we will use these and relate them now to rate factors. Rate factors are those factors, if you change, will change the rate of reaction. There are 5 rate factors that we're going to study. And it's really easy to remember these. Now, this is not a concept, principle, or published miracle or whatever. It's an acronym that helps you remember these. C, A, N, T, C. Can't see. An interesting acronym. But the C stands for concentration. A is area, that is surface area. N is nature. You change the structure of a molecule, you will change its rate, and we'll do a demo on that next week. Temperature and energy. And catalytic effects. If you change concentration, you will change the rate of reaction, maybe. And we'll show you that in a minute. Or if you change the area, like you have a log you're trying to set on fire versus small kindling. And I think everybody understands that you can ignite kindling a lot easier than you can light a big log because the surface area is higher. Nature is a structural characteristic, and the structure, chemistry of the molecule and its ability to react is dependent on that structure, its bond strengths and so forth. We'll show you that in a demo and an illustration. Temperature and energy, raising the temperature. I think we all know that raising temperature increases the rate of reaction. Why? Because we cook our food. It's not going to cook itself. And so we raise the temperature and it undergoes the reactions necessary to give us nutritional food. Catalytic effects. A catalyst is something that changes the rate of reaction by changing what is called the activation energy. And some of them will increase activation energy and slow a reaction down. Some of them will decrease activation energy and speed of reaction up. But the catalyst in itself in the reaction is never consumed. And we'll show you how that functions in what we call chemical mechanisms. Okay, in this section, remember, as can't see, one of the rate factors is concentration. So what we're looking at here is concentration effects. On reaction rate. There are four kinds of problems that you will have to learn about in this topic. One, rate averaging. Rate and reaction coefficients. Empirical rate laws or experimental rate laws. And what we call the integrated rate laws. Also known as the decay process. Rate averaging is very simple type problem. It's based upon the definition of reaction rate, where rate is defined as a change in concentration, molar concentration, over a change in time. So in the problem that's given, you'll be given a concentration at time 1, concentration at time 2. You just simply apply it to the definition. This first problem is an example of that. Iodide ion is oxidized by the hypochlorite ion in a basic solution according to the following reaction. Determine the rate average if a 1 molar sodium hydroxide solution, the iodide concentration at different times are as follows. So like I said, you're given a concentration at time 1, a concentration at time 2, and you simply take the difference in concentrations divided by the difference in time. So your rate average is your change in iodide concentration divided by change in time. So that is the expression that defines that rate. And initially it starts at 0.00169 molar and ends up at 0.00101. And I need to turn that around, sorry. Second minus the first. See you in a moment. So we start at what I gave you, 0.00101 molar, and end at, I began at 0.00169 molar, and it's 8 minus 2. And that's in seconds. Now, in the computation of rate average, it's going to come out negative. Okay, of course, it simply interprets as you having a decrease in concentration. But there is a controversy about this. Rate doesn't have a sign. That's my opinion. you're going 60 miles an hour, and down the road, you're going 60 miles an hour. If you change that rate, that's called acceleration. Okay, and that's a change in the speed over time. So when you write this out, when you make this calculation, run it out real quick for you. We get a negative 0, I'll put it in decimal, 0.000113 molar per second. Now, some people say, yeah, we're decreasing. All you can say is that indicates you're decreasing concentration. As you change your speed, as the rate goes along. But what the textbook tells you, Ebbing tells you, is report rate as an absolute value. So, therefore, the rate average should be reported as a plus 0.000113 molar per second, or just no units at all. I mean, no signage at all, because that's what it's doing over that average. It's a rate. Some people argue the issue, and some people don't. Test day is going to give you both a positive and a negative. Well, the reported answer is positive. So I'm telling you, in this class, we're going to report rate average as positive values. Make it that. When an equation is written, it's written in basic standard state, the molecular equation, that is. And so we take something like 3H2 as a gas plus N2 as a gas and produce 2NH3 as a gas. Now, if you want to define rate of change in concentration as a function of time of each of these compounds in the reaction, you write this in the following way. Change in molar concentration of H2 gas over change in time. That's for hydrogen. Change in nitrogen gas over change in time. And then you have a change in ammonia gas over a change in time. So each one of these represents a rate. Now the second thing here is, what's the relationship between hydrogen and nitrogen rates, nitrogen and ammonia rates, or hydrogen and ammonia? Well, if we take the rate of hydrogen and the rate of, say, nitrogen, it's easy to see by the coefficients that hydrogen is being consumed 3 times faster than nitrogen in this reaction. So the problems that you have will be like those that we did in molarities, where you swap coefficients, and then you do the same thing here. What you'll need is to take these two terms, and the problems are always in terms of just 2 at a time. You'll have hydrogen, nitrogen, or hydrogen, ammonia, but you won't have all 3 of them tied up in one equation. So what you do is you rewrite your rate expressions and set them equal. Give you a little space here, because you're going to swap coefficients, and then they're equal. And problems will give you at least one of the two rates, and then you solve for the unknown. Okay, so the coefficient of nitrogen is 1, so we'll put a 1 over here. And the coefficient of hydrogen is 3, so we'll put a 3 there. So now, if one of them is given in the problem, you solve for the unknown. See the point? And then you can write other relationships out of this. Here's hydrogen, nitrogen, and then hydrogen and ammonia. So you have hydrogen and ammonia. And you want to set that equal to change in ammonia. Like this. And this one has a coefficient of 2 for ammonia and 3 for hydrogen. Well, to make those equal, I will swap the coefficients, and one of them given, you can solve that little expression for the one that's not given, and so forth. So you'd have, let's see if I can get all three of them in here. I would have hydrogen, nitrogen, hydrogen, ammonia, nitrogen, and ammonia. So I'd have change in N2 gas over change in time is equal to change in ammonia gas, change in time. The nitrogen is 1, so we'd put a 1 in front of the ammonia expression, and we put a 2 in front of the nitrogen expression. So, like I said, they're always given in pairs. The unknown, of course, is a simple solution of a linear process right there. Okay. Let's look at calculate the rate at which N2O4 is formed in the following reaction at the moment in time when NO2 is being consumed at that rate. See, they give me one rate of this combination. And so you write the rate expression, set them equal, and swap coefficients. Then substitute the given and solve for the unknown. So in this problem, we've got 2 NO2 as a gas. Now I got solid in this, not a gas. No, that's a long equation. Goes to 1 N2O4 gas, and so we want the change in NO2 gas over the change in time, and we want to set that equal to the change in the N2O4 gas over change in time, and swap coefficients. So we have a 2 there and a 1 there. Well, according to the problem, the NO2, that's this one, is being consumed at 0.0592 molar per second. And that's 2 times the change in the dinitrogen tetroxide. So, and the change in N2O4 over time is therefore equal to 1/2 of the 0.052 molar per second. And so just to be sure. So that is the first two problem types. Now we'll start tomorrow with the concentration and go through the integrated rate laws and as far as I can go through the kinetic molecular theory and energy changes, and we'll cover as much as we can tomorrow, and that will leave us Monday for equilibrium. And so equilibrium is quite voluminous in itself, and so just be prepared.